There is a third way to find the endpoint in a titration. So we've got the two that we've covered so far, which is the traditional way of using indicators, and we've seen that's fine, but you've got to be careful. And there's the idea that you can actually use the titration curves and monitor the pH, and that's easily done using an electrode connected to a pH meter. You don't need to know anything about how pH electrodes work, but you need to know of their existence. But as I say, there is a third way, and that is to exploit the fact that the neutralization reaction, so that, the essential reaction is, this, has an enthalpy change of about minus 58 kilojoules per mole. So it's an exothermic reaction, and that means that when you do a titration, the solution warms up. And if you do it with reasonably concentrated solutions, it warms up enough that you can conveniently follow the temperature rise, and it turns out that you can use that to determine the end point in a titration. So the idea would be that you would have your solution there with some kind of stirring bar there, and dipping into the solution you would have a thermometer. So obviously it's important to stir it because you can't swirl it really with the thermometer in there, but you can use a magnetic stirrer thing to do that. And using that setup, you can generate data which enable you to plot a graph of the temperature as a function of the volume of alkali added. So if you think about what's going to happen, every time you add a given volume of alkali, say 1 cm cubed of alkali, it contains the same number of moles, so the same number of moles will react with acid to produce water, and therefore the same amount of heat will be added to the mixture. If the volume was constant, therefore the temperature would rise in a linear way, because you know that Q is equal to MC delta T, and so delta T is equal to Q over MC. So if the mass of the solution were constant, then because you're adding the same amount, so as you do the titration, each cubic centimetre of alkali that you add will obviously contain the same number of moles of alkali, and therefore when it reacts with the acid will generate the same amount of heat. So you can see that if the mass were constant, then as you add the alkali, the amount of heat added to the solution would rise in proportion to the amount of alkali that's reacted, and therefore the temperature would also rise in proportion, and so you would get a linear rise in temperature like that. Now in reality, of course, the mass is increasing as you add more alkali, because the total mass is increasing as you add the second solution to the first one. And you can see that if M gets bigger, then delta T gets smaller as time goes on. So really, that's not going to be linear, and it's going to sort of go something like that. However, to make things easy for you, at A level that gets ignored, and so you can assume, for the purposes of A level questions, that you get a linear temperature rise. And you could achieve that in reality by adding a much more concentrated solution than the solution in here, so you are adding much smaller amounts volume-wise of this than there were of this, so that in percentage terms the volume didn't change much. But anyway, for whatever reason, you get a linear rise. Until, of course, all the acid is gone. Because you're adding alkali and it's all reacting, and at some point there will be no acid left to react, and at that point the temperature's not going to rise anymore because there's nothing for the added alkali to react with. And so the temperature will abruptly stop rising. It won't just curve, it will just abruptly stop rising. And as you continue to add more alkali, of course the temperature won't just stay constant, because you're adding cold alkali to a solution which has now warmed up. And so what's actually going to happen is that you get something like that. Okay, so this is the equivalence point. Okay, because that's the point at which you've stopped getting any reaction as you add more alkali, so no more heat's being generated, and you're just cooling the overall solution down because you're adding cold alkali into it with no reaction to compensate for that. So that sharp break there gives you in principle a very good way of finding the equivalence point. Now of course in reality when you do an experiment like that, the chances are you won't be adding it continuously and measuring it continuously. What you'll actually be doing is adding it in small increments. So what you'll get is an initial temperature and then, you know, a sort of increasing temperature like that measured in bits at a time, and then you'll get a decreasing temperature once you go past the end point. So the question is, okay, you can see what's happened there is that we've missed the precise end point because it's going to be somewhere between there and there. And the question is, well, how do you find it? And the answer is you draw two straight lines and you look for where they intersect. So you don't try and draw a curve, you draw two actual straight lines going through those points. So if we do that, here we can draw a straight line that sort of fits through those points as best we can, so something like that. And then we do the same here and fit those points to a straight line as best we can and get something like that. And it's where those two straight lines intersect that we say, right, that is the equivalence point. So that's something you might get to do in an exam, because they could well give you a graph like that with just the points marked on it, and what they want to see is that you realise you draw the two straight lines because there's an abrupt break in the trend there. It's not a sort of curving in between. So that's fine because that gives you the volume, and then you can do the normal kind of titration calculation. But of course there's something else you can do, and that's use the data to find the enthalpy change of neutralization. Because this is our starting temperature. Okay, so that's our temperature at the beginning, and this is the temperature at the equivalence point, and so that is delta T. So we can do Q equals mc delta T in the usual sort of way. M will be the total mass of the solution at the equivalence point. Okay, because we're looking at the total temperature rise just up to the point where we've reached equivalence. So M is the mass of solution at the equivalence point. And usually, remember, you work that out by assuming that the mass in grams of the solution is equal to the volume in cm cubed. In other words, you assume a density of 1 gram per cm cubed, which is a good approximation for aqueous solutions in general. Okay, so that's what we're going to do. Assume that the mass is in grams is equal to the volume in cm cubed. That's what you most commonly do anyway. C again comes from your data sheet, and you've got delta T, so we can work out the amount of heat that's transferred. And of course, provided we know what the concentration of one or other of the solutions was, and we know its volume, we can work out how many moles reacted, and so we can do the normal thing of delta H will be equal to minus Q over moles, minus because it's an exothermic reaction, Q is the amount of heat transferred, M are the moles reacted at the equivalence point. And that will give you delta H of reaction. Remember, if you want delta H of neutralization. That has a very specific definition. You need to look back in the first year where we introduced enthalpy to learn that. That's the delta H per mole of water formed. So if you're working out delta H of neutralization rather than delta H of reaction, when you put moles in there, it needs to be the moles of water formed once you've reached the equivalence point, rather than the moles of acid reacted or alkali reacted. So you've got to be careful with the wording of the question. But that's basically it. That's all you need to know about this method. It's called a thermometric titration. Okay.